Hello, everyone. My name is Arturo Gamboa, and today I will speak about my project, CSCI 104 Advanced Deep Learning. And I will speak specifically about what is flash attention, and I will present a benchmark of how flash attention really is the way to go when it comes to training very large LLM models. So let me give you an example to understand how flash attention works. So imagine a teacher trying to gather end of the year feedback from 500 students in her classrooms. In the traditional approach, the teacher hands out surveys to each of the students, collect all the responses, and then analyze every survey at once. It's gonna be very slow. It's gonna be memory intensive. It's gonna be labor intensive, but it's gonna get done at some point. A smarter way to do this is to meet with the students in groups, in smaller groups, maybe the 10 or 20, and then take notes and move on the next group, extracting the meaningful feedback for that specific group without really knowing or taking care of who the student is, which is ultimately she wants to take feedback so she can improve next year. So a smarter way to do that will be basically break down in groups and take the meaningful feedback and move on until she finishes with the 500 students. That's exactly how flash attention works. The second approach, which is flash attention, is more efficient, is faster, easier on resources, and is exactly how the efficiencies of flash attention come to fruition. So today I will show you how FlashAttention2 improves performance, memory usage, scalability using real benchmark visualizations on my NVIDIA H100 GPU. If you ever wonder how modern languages models scale to over 100,000 tokens without overwhelming your GPU, FlashAttention is the answer. So the standard attention, as you can see here on the left, becomes very expensive as the sequence length grows, both in compute and memory and time and resources. Every query attends to every key, leading to a quadratic explosion in operations in compute. Flash attention solves this problem by computing in a very memory efficient way by breaking down the matrix in tiles, fusing operation and maximizing the GPU utilization without changing the math. So in a regular attention environment, we compute the entire matrix. You can see Q, K, and then we compute this product, which is very expensive because you have to compute this and you have to save this in memory. Flash attention does the same math, but in a smarter way. It breaks down the attention into tiles. This could be one tile, this could be another tile, and then extract the meaningful weights, the weights that is important of that tile, and without saving it, compute softmax and multiplication, matrix multiplication fusion. It does that very efficiently, and when it's done, it moves to the next one. That's how flash attention really is a game changer when it comes to efficiency, time, compute, and it's just a game changer in general. Let me now speak about the hardware that I'm gonna be used for my presentation today. So we're talking about the project was run in my NVIDIA H100. It's one of the most powerful GPUs available in the market today. It supports a brain float of 16 precision, tensor cores, and full compatibility with FlashAttention2. I also use PyTorch with FlashAttention enabled, and I generated synthetic tensor simulating real world-class LLM workloads. So we can really see how FlashAttention really solved that problem. I use also matplotlib and animation code to create the visualization that I will show you today. So let's talk about the configurations very quickly. Here are the configurations I use. These configurations are all synthetic, but designed to closely match the type of tensor shapes using very large transformer models like GPT or Llama. Each input tensor has a shape of batch size. You can see here batch size sequence length, number of heads, and head a dimension head. You can see here, I use very long sequences just to challenge 8,000, 6,000, 65,000, and over 130,000 length of tokens. That's insanely long sequences, and we want to see how FlashAttention handled those really nicely. Each of these was run through the same benchmarking pipeline. I run it the same for regular and Flash, and then now we can compare the results. So here are the results. You can see here immediately how the speed up was almost twice for the very long sequences. You can see here the sequence, and this is the sequence length, and then the speed, how the speed was almost double in time. And you can see here the massive benefits also in number of tokens processed, the payload, which is massively on each of these, regular versus Flash. I'll show you some plots that you can see here. Pretty much in all 6 configs, we can see speeds almost double on benchmarking regular versus FlashAttention. You can see almost twice the speed as fast. Really impressive. On the number of throughput tokens, you can see here, you can see immediately how much the tokens was processed. Is in all cases, FlashAttention just destroy regular attention. You can see a comparison of memory after with the two of them. With that very long sequences, you can see here that these two are the largest ones. The memory was just there. So now let's talk about very quickly about how FlashAttention really works, so you can see it in visualization. So let's take a look at this, how this animation works. I'm gonna run it. This animation shows how the model attends to the different tokens frame by frame. The yellow areas show the attention weights as the model is executing. The dark areas are the low areas or the low attention weights. We visualize attention. We visualize attention for each query position as it moves through the sequence. This was generated using FlashAttention2 output by manually extracting attention weights and turning them into the video to help visualize the behavior over time, so we can all see it. This is just one head. Now I'll show you 4 heads in action, which is pretty much the same thing. You can see here how the FlashAttention moves from left to right and how everything is computed. You can see this as just for the purpose of demo this, I use a sequence of 64. But imagine that we use this, you just plug this number in your head, that instead of 60, we put this, it will be very long from left to right. But this is how everything works for every head. So now let's walk very quickly about the time comparison. This is really impressive, because you can see here, I'm gonna run the video. Here's the runtime comparison between regular and FlashAttention. You can see how long each method takes on different configuration. FlashAttention consistently runs faster, especially for the very long sequences that like a 65,000 or over 130,000 tokens, which is this one last. You can see the difference is massive in speed and time, how fast it's doing it. Now let's explore the number of tokens. So you can now see the number of tokens processed, basically the output produced, how many tokens are produced, regular versus Flash. You can see here the benchmark. The benchmark is crucial. This is crucial for large scale LLMs. FlashAttention destroys the regular attention. Just look at it. It's just in all configurations, FlashAttention consistently produce a lot more outputs in tokens when it comes to regular. Now let's quickly go to a benchmark of this, so we can now see how the whole memory impacted versus the memory used on each tile. As you can see, FlashAttention, it doesn't use memory when he's computing each tile and softmax and multiplication because of the fusion. Everything is done until it's done without saving into memory, which is a massive benefit how all the efficiencies are done. And you can see here on regular versus flash, how basically the flash attention is almost none, while regular is requiring this because the whole compute is being done, which is massive, intensive in resources, memory, compute, everything, which is the regular attention. Now, let's quickly go to casual, non-casual attention. And here we can see, you can see in some cases in transformers, we sometimes use casual masking, meaning each token can only attend the past and not the future. This is crucial for tasks like text generation. The animation shows the difference. With casual attention, the upper triangle is masked. With non-casual attention, every token can see every other token. Flash attention support both casual and non-casual attention. Now, in conclusion, let's just quickly go to this. You can see that flash attention does the same math as regular attention, but is computing a much faster, much smarter, and very memory efficient way, saving in time, compute, and resources used, specifically memory. And those are massive benefits when you are dealing with a very large LLM models, like all the large, very large LLM models we have seen, Olama, GPT-4, GPT-4.5. This is a game changer, flash attention. I have this whole notebook is gonna be uploaded on my GitHub repository. Feel free to watch it. Thanks for watching, and I hope this guide gave you both technical insight and visual intuition how flash attention works and how is a big game changer. Thank you very much, and thank you for watching.